All right, so just to remind you, everything that we've done, and what I'm going to do at the end, guys, is I'm going to sum it up for all the different situations that we have, just so you can see it all condensed into one spot. Okay, but for the most part, everything we've done for the past few days really revolved around that. Now there was, right, alternate things that we've already talked about, right? If you had an equilateral triangle, we had a side length, there was a formula for that. If you had a hexagon, they had a side length, there was a formula for that. So, but for the situations like on Friday where you had a radius or a pop or a side length, you had to go back and do 1/2 AP. Okay, or if the shape wasn't a hexagon, you had to do the 1/2 AP. All right, so it revolved around that. It's just as we've gone through, I've tried to point out maybe times when you had a shorter way to go through the problem, such as equilateral triangle or hexagon. Okay, now there's going to be another way today that will probably give you a shortcut in terms of finding these things. No, it's pretty straightforward. All right, but what it revolves around is this other formula for area of a triangle. Okay, now with this formula right here, guys, this is going to be a situation where you've got a triangle, you know two side lengths, you know the angle in between them. Okay, and instead of taking the time and drawing in like a height and wasting time trying to figure out the height of that triangle and do 1/2 based on height, okay, this saves you a good bit of time if you have the following situation where you've got essentially, if you've got a triangle, okay, it's the same kind of triangle we give with law of sines and law of physics. If you've got a situation such as the one right there, I've got two side lengths, and I got the angle directly between them. All right, if I didn't have this formula to work through, and it's derived from essentially breaking this triangle up into based on height, like drawing in the height, using trig ratios to find the height, and so on. But you know, I'm not going to have you guys do the deriving of it right now. Okay, but essentially what this breaks down into, guys, is if you have this situation, instead of wasting the time drawing in the height, taking time to find it, using sine, cosine, tangents, whatever, okay, you can simply use this formula right there, okay, where the A, B, and C correspond to whatever's on that picture. But it essentially becomes, you do 1/2 of whatever the two sides you know multiply together times the sine of that angle. So this is all multiplied together, there's no adding, subtracting. It's 1/2 the two sides you know multiply times the sine of that angle. Okay? So and what this is going to do is I'll show you how it corresponds to the area of the polygons, the regular polygons. All right, and I'll show you which situations you will use this in to kind of save time. All right, and if you don't do it this way, this is just going to be a shortcut way today. If you don't do it this way and you stick strictly to what we did on Friday, in terms of drawing that one right triangle and just solving out the sides of the right triangle, that'll get you the right answer every time. Okay, so again, this is just going to be a shorter way to do it. All right, now, you are going to have problems based strictly on this, so there are going to be problems today that aren't regular polygons that are going to be find the area of this triangle. All right, but they're pretty easy. Okay, they're simply plugging numbers into that form. You just, like I said, you just have to remember you're doing two sides and the angle that's between them. So if you want to correspond it to stuff we said before, it's like side angle side. Okay, where that's the included angle because it's touching both the sides. All right. Go past it. And I'm going to go through probably two problems, guys. I'm going to have you do a couple in the book, and then we'll go into the regular polygon stuff. Go on now. Good. Good. These right here will be just two examples of when I would apply the formula. So like if I gave you both these triangles and said, find the area of the triangle. Obviously I don't have a height there, so I can't do 1/2 base times height. I could draw in the height, like I could take the time and draw in the height, right, and try and work with it. Wouldn't be an issue. Like I could, on here, I could take the time and draw in like this side right here, make it a height, and then do like, sine, cosine, tangent stuff to get that side of it. It's just not necessary to do it because of the formula which is up there. So if I wanted to find the area of this, all you would have to do is go, well, I've got two sides, that angle directly between the two sides, my included angle. So all I have to do to get the area is just go 1/2, 8 times 3, times sine of 50. That's it. A whole lot quicker than drawing in the height and taking the time to find the height. All right, so multiply it out. All right, what is it? 4 times 3 times sine of 50. That's right in the calculator. All the way through. 9.2. Yeah? Yeah, that sounds about right. 9.2? Yeah. Okay, so it's the 9.2. Right? Can I do the same formula with the one on the right? Could I? Yeah, I've got two sides, got an angle between them. If I was doing this, 9 times 9, times sine 65. Like this formula, guys, you just got to remember, this is only in a very specific situation. Okay? 81.6. And the whole trick to doing most of these area and perimeter problems is recognizing the situation and when to use it. Obviously, the situation here would be two sides to include angle. If I was still doing equilateral triangles, guys, I would still do the equilateral triangle formula. If I've got a base and a height, I would still do 1/2 base times height. Okay, it just all depends on what's given to you. What I'll do first is I'm going to show you guys everything we've done so far, but I'm going to try and categorize it so that you've got it into the different situations. Okay, starting with like the first thing we did with the special situation was the equilateral triangles and the hexagons themselves. All right, so where we're at right now, before I do the stuff applying this, and this is, guys, this is all of the area of the regular polygon stuff. Okay, so the situations we've got is we have a formula for, right, equilateral triangle given a side length. Okay, and remember, it's only if you're given a side length. And this was the area is, so that was like the first special situation when we did. Okay, talking about just alternates. Because I said that the key to doing this is figuring out which situation you're going to use these in. Like you have to be able to look at a problem and tell which thing is going on. So you don't always do the 1/2 AP. You can, even with this one, you could go back and do 1/2 AP, the thing we did on Friday, and get the right answer. It's just quicker doing this. Okay, you're not going to waste time. All right, so next one would be a regular hexagon given a radius or side length. Okay, and remember, you could have either one of those because this one was the idea behind the hexagon was right that it's made up of equilateral triangles, so radius of a hexagon is the same as the side length. So this one was the 6, right? It was, remember, it was just the equilateral triangle formula times 6. The hexagon was made up of the 6 equilateral triangles. All right, and then the other ones that we've done up to this point would be just the general regular polygon, and I'm going to limit this to given either a side length or apophysis. Okay, I'm not bringing up radius because that's what I'm about to add to this. Okay, using the new formula. All right, and this would be, and again, when I mean regular polygon, I mean like anything that's not fitting into these two categories up here. So pentagons, octagons, decagons, whatever. All right, and this was just 1/2 AP. Okay, so even after the stuff we're about to do, you know, if I give you a problem and there's an apothem, you still need to do that triangle set up where that's the radius, right? That's the apothem. That's the 1/2 side, and that's still 180 over. Okay, that stuff never changes. All right, the last thing is going to be if you've got a regular polygon, given a radius. Okay, there's two things you have to kind of do with problems like this. All right, and I'm going to raise this top part. Okay, so all right, so in general, here's how we're going to apply this. With this shape right here, that'd be a pentagon, correct? Right?
Yeah.
That would be a radius, right? That I've drawn in here, that is a radius, correct?
Yeah.
Okay. They're both exactly the same, right? So you would agree that they are isosceles triangles, right?
Yep.
Do I know how to find this angle right there? How? Wait, the 360 over n, right? Because that's the central one. It's not the 1/2 one over here because it's not that half. All right, so that angle right there would be 360 over, in this case, 5, correct?
Yep.
Which is 72. If I put a number on this side, like, just give me a number, I don't care.
30.
14.
Well, what was the first one? If I got that side as 12, do you agree that side is 12?
No.
Yeah.
That triangle right there, if I drew it by itself, it would be 12, 12, 72 degrees. Would that technically fit the thing I just did with the area triangles?
Yeah.
Yeah. So the whole idea with this one here is if I know the radius, I'm basically creating an isosceles triangle and I know how to find the angle right there. And what you're going to do is if I do the area formula I just had, which in this case would be 1/2, 12 times 12 times sine of 72. All right, that would give me that whole thing right there. All right, and if I drew in every radius that's up there, would all these triangles be exactly the same? Yeah. So all I'd have to do really to find the area of this one, instead of doing the work we would have done here on Friday, all I have to do is that formula, which is one triangle, and then multiply it by however many triangles are there. Okay? So if I was doing like this problem with the pentagon, I would find this number here, which is what's this one?
But like in many types of problems, will they give you like a side one?
So it has to be this situation,
Oh,
only that
okay.
situation. What is all this stuff multiplied together? I don't know. What? 60. Okay. 0.5?
Yes. 68.7.
7? Wait, hold on. Is it 5 or 7?
5.
Don't trust them.
Wait, how's 5 round to 7, 7 round to 5? Doesn't make any
I
sense.
said it wrong.
68.5? Okay, definitely. All right, so if I was doing this problem, I would say, look, this one triangle, area is 68.5. If I want to find the area of the pentagon, multiply by 5.
Is this going to be on the, is this going to help us with the like?
Yeah, all this stuff that was up here, gone. What's 5? Wait, what is all that?
42.5.
Wait, 3 what? 42? 3?
No, actually, it
Kill me.
is.
I'm going to throw something. Okay, now here's the thing. If I took all the stuff I did up there and put it into a formula, all right, for area of a regular polygon given a radius. Here's how it would kind of look. You'd have n, right? It's the number of sides, correct? Divided by 2, because I'm doing the 1/2 from that formula, right? That was the radius, correct? Right?
No.
Yeah, that was the
no,
radius,
no.
right? So, is that okay? Radius squared, because they're both the same, so multiply them together, squared. And then it's sine of, because remember that the sine of the angle you're taking is always the central one, which is 360 over the number of sides. Okay? So if I did another problem, if I said, find the area, the regular, I don't care how many sides. How many sides you want to have?
10.
8. Go beyond like
27.
12 sides. No, you're going to make me actually write that. Who's the actual guy? The radius of
19.5.
13 what?
27.
Oh, 13 what? Units.
Meters.
Meters?
I like our
Huge, dude. I think it's huge. Okay, so here's the thing. I've got this condensed right into one formula here. But usually with this method, it's easier for people to remember, do the triangle, and then multiply by the number of sides. Okay? That's usually the easier thing. This is just what it would look like condensed into one thing. So like if I went in there and set it up using that formula, it would look like 13 over 2. I mean 12, sorry, I just saw 13. Yeah, it's 13 squared times the sine of that. But like I said, it's usually easier if you're doing this to remember I'm working with the triangle that looks like that, right? And then I do 1/2. I don't care how you do it. Get the right answer. Okay.
All that.
That's fine. Get the right answer. That's what you need to worry about. All right? It's like I said, normally if you're doing this way with the radius thing, it's easier to do it this method. Like say, I need to find the triangle, and then whenever I get that triangle, I'm going to multiply by however many sides of it. Okay? That's usually the easier thing to remember. All right? But it doesn't matter either way you do it. I trust you guys.
I got 42.5
Times 12.
times 12.
This one, hold on.
570.
Okay? All right, so guys, hey, this is just, look, if you don't want to do it this way, it doesn't matter. You can still do them this way right here if you've got the radius, like we did the other time. It's just, with this method, remember you're doing sine and cosine to find the half side and the apothem. That's just quicker, okay? All right, so it's, but again, this is only if you have the radius, all right? If you've got the apothem or side length, and it's not like equilateral triangle or hexagon, you have to do that work. Okay, this is just one other situation. There's 4 different ways you can approach these, okay? 4 different things that could happen.